Hello, everybody, and welcome back to another Mr. Farney Earth Science video. This video, we're going to be looking at how scientists measure and locate earthquakes as the third section, the third video in our earthquake unit. So diving right into this, the main idea is looking at how scientists, they measure the strength of an earthquake, and we're going to learn two terms, magnitude and intensity. We've been using the word magnitude in class. But we're finally going to give it a definition outside of just a random arbitrary number. So we'll talk about magnitude, we'll talk about intensity, we'll take a look at a couple of different types of scales that scientists use in order to gauge the strength of an earthquake, and we'll briefly talk a little bit about how scientists use the seismic waves to assist them in determining where the epicenter of that earthquake was located. So getting right into it, we've used these words, we've spoken about magnitude in class, especially with our USGS earthquake lab, but we haven't really given much definition to this word intensity. So here's the difference between the two. The magnitude is the measurement of the amount of energy of the largest seismic wave produced by the earthquake. So the magnitude, that's our energy measurement. Intensity, that is determined by the size of the surface wave, or what we refer to as the amplitude. So magnitude, that's our energy measurement. Intensity, that's measuring the amplitude of the surface waves. So with regards to magnitude, we used to use the Richter scale. Now, some places still use the Richter scale to measure the magnitude of earthquakes, but the Richter scale is only more or less accurate up to about a 5.0 earthquake. Beyond that, we use a different scale to get a little bit more specificity in there. Intensity, this is how much shaking is going on the ground in proximity to an earthquake when that surface waves pass. This intensity will decrease the further away from the epicenter that you are. If you think about this like an ocean wave coming and crashing onto the shore or the beach, as that wave approaches, it's very big, it's very intense. As it hits the beach line or the shoreline, it gets smaller, and then it kind of spreads out until it hits a point where it no longer exists. That intenseness of that wave decreases over time the further you are from that crash point. With earthquakes, that intenseness, it reduces the further you are away from the focus or the epicenter of the earthquake. So magnitude, energy, intensity, shakiness, rumblies, if you will, of the earthquake. So it's good to kind of differentiate between those two terms. The Richter scale is the kind of the most prevalent or the most well-known scale used to measure the energy of an earthquake. On the Richter scale, which I'm going to jump to this next slide, it works off of a magnitude or longitudinal kind of system where every mark or every deviation you go up on the scale, and it increases tenfold or goes up 10 times. What does that mean? Well, if I start at 0 and I go to 1, 1 is 1 times, or 10 times, I should say, stronger than a 0. A magnitude 2 earthquake is 10 times stronger than a 1. Okay. A magnitude 3 earthquake is 100 times stronger than a 1. Magnitude 4 is 1,000 times stronger than a 1. Magnitude 5 is 10,000 times stronger than a 1. Magnitude 6 is 100,000 times stronger than a 1. Magnitude 7 is 1,000,000 times stronger than a 1. Do we kind of get this? But then if I were to move up the scale and compare like a 7 to an 8, that 8.0 earthquake is only 10 times stronger than the 7. So the strength of these earthquakes compared at different sizes, it's relative to each other. So you just have to pay attention to where you are on the scale to kind of be able to figure out how much stronger an earthquake is than another. So if I were to ask you, how much stronger is a 7.0 earthquake than a 5.0 earthquake? I'll pause for a second to let you think of an answer. What are you thinking? If you're thinking 100, you're thinking right. This 7.0 earthquake is 100 times stronger than the 5.0 earthquake. That 5.0 to the 6, it goes up 10 times. From that 6 to the 7, that's another 10. So 10 times 10 is 100. That 7.0 earthquake is 100 times stronger than that 5.0. So Pay attention. Hopefully you understand that. If you have a question about that, let me know, because that is a concept that you will see at some point. Hint, hint, wink, wink. Okay. This other scale, the moment magnitude scale, is much better at forecasting larger earthquakes. The reason is the technology has gotten better over time to measure the earthquakes since Mr. Richter, or Dr. Richter, I'm not sure if they were a doctor or not, came up with the scale, the original longitudinal scale for measuring earthquakes. We have computers now, we have better technology. Technology in science always drives the change from hypotheses to theory. And it's what makes it kind of spring forward. So in this instance, we have a much more accurate measurement scale in the moment magnitude. On the right-hand side here are several earthquakes that have been recorded on the moment magnitude scale, including the Southern Chile 1960 9.5 earthquake, the strongest earthquake ever recorded. The strongest earthquake ever recorded in the United States is the 9.2 Anchorage, Alaska earthquake of 1964. So again, moment magnitude uses more variables to calculate the energy released during what's called the seismic moment, which we'll talk about in a second. Don't worry too much about that right now. Here's a great picture that shows the strength of earthquakes and the energy equivalents to other things that we've seen. So looking at the right-hand side here, an average tornado, the amount of energy that is produced by an average tornado is just shy of a 5.0 earthquake. The Hiroshima bomb that was dropped on Hiroshima in World War II, that is just a little stronger than a 6.0 earthquake. Mount St. Helens, a little weaker than an 8.0 earthquake. The largest nuclear bomb test by the former Soviet Union was just about an 8.0. Krakatoa, that one volcanic eruption that happened, that was one of the strongest volcanic eruptions in history, about an 8.5. All of these, not even close to that 9.5 Chilean earthquake. So if we're looking at this, where the Hiroshima bomb is a little more than a 6.0, and the Chilean earthquake is about a 9.5, that means that Hiroshima bomb, compared to that earthquake, a Chilean earthquake was 1,000 times stronger as far as energy released than the atomic bomb dropped on Hiroshima, Japan. That's incredible to think that the power of the earth, regardless of human technology at this point, the strength of nature and earth itself totally overshadows anything that we can produce as a species. So that's just incredible. So this is a really good chart to kind of compare and contrast earthquakes that we've seen and measured, comparing that to things that we know, like lightning bolts or different types of, atomic weapon testing or other volcano eruptions. So really good chart. Again, I mentioned this already, moment magnitude versus Richter. It's technology advancement that's really making things more precise and much more accurate. We have faster computers. We have way more sensitive seismometers that'll enable scientists to record and interpret a much broader spectrum of these seismic waves than was possible in the 1930s when that Richter scale was developed. It makes sense that we're trying to get away from the Richter scale to improve upon it. That's a technology that at this point is almost 100 years old. It's about 91 years old from right now. So it makes sense that if we have better technology now, technology that helped us get to the moon 30 some years after this scale was developed, that we'd have more precise measurements. Here's a fun fact. If you remember back to our plate tectonics unit, we were talking about Alfred Wegener and Harry Hess. The idea of plate tectonics, it wasn't accepted as a theory until 30 some years after Richter developed this magnitude scale. So that just shows how much technology and how much kind of scientific development has come to pass since the development of this scale. So it makes sense that we want to make improvements on it to make it better, so we can have better records, better measurements, and maybe even at some point develop a better forecasting method than we currently have for earthquakes. Again, this slide right here just hits some key points that the Richter scale is effective for, localized regional earthquakes, no larger than 0.0 magnitude. The moment magnitude scale is much better at larger earthquakes because it uses more variables to calculate the energy released during that seismic moment. Now I have that word underlined and it's on our study guide as a vocabulary word. I'm not necessarily going to test you on it, just, add it to your vernacular so you expand your common knowledge. That's how much force is needed to generate the recorded waves that we see on seismographs. So how much force is generated. So just another fun little science term to throw around. One thing I want to point out is that this slide, and this slide, all 4 slides of moment magnitude, they are not included on that follow along note sheet that I provided at the beginning of this unit. I just added these slides in because I felt we needed some more information about this more modernized measurement system. So you want to go ahead and add this to your follow along notes or to your own notes, because these slides did not exist on this PowerPoint until right before I started recording this. Essentially, I added these yesterday. So very new slides, very important information. This last scale here, the modified Mercalli scale, this rates earthquakes based on how much damage is produced by them. It's very similar to the EF scale that meteorologists and atmospheric scientists use to determine how strong a tornado was after a tornado event. If you didn't know, the way they gauge how strong tornadoes are is they do not wait until they see the tornado and try to figure out, oh, it's an EF1 or an EF2 based on how big it is. Yes, that can give them some information, but they don't have an accurate measurement system for currently on the ground tornadoes. There are too many variables in play for them to be able to do that currently with what we have. There's technology that's getting better, but what scientists still do with tornadoes is they wait until that tornado passes, then they go into the areas and they take an analysis of the types of damages that were done by that tornado event. The modified Mercalli scale, it uses the same methodology. After an earthquake happens, scientists go into the area, they take a look at the damage that was done in that area by the earthquake, and based upon the intensity of the damage, they rank it from 1 to 12 using Roman numerals here. So that can range from recorded only by seismographs as a 1, felt by some people, some slight building damage, great damage where we get buildings collapse, all the way up to total complete damage. You literally see the seismic waves on the ground, which throw objects up into the air, up as a 12. The next slide compares and contrasts what this looks like with the modified Mercalli on the left, Richter on the right. If you want to kind of, go all the way down to where some of those much larger earthquakes were, like our 9s, like a Chilean earthquake, 8.0 and above on the Richter scale kind of falls under that 11 and 12 on the modified Mercalli, with total destruction, waves seen on surfaces, objects tossed and tumbled, huge cracks are visible in the ground. So very kind of neat little extra bit of qualitative evidence that they can use just to describe what happened during some earthquake event. So those are our different scales that we have. We got the Richter, we have the modified Mercalli scale, and then we have our moment magnitude scale right there. Very important to kind of recognize the difference between those scales. One of the last things we'll talk about, and we already briefly looked at this in the seismic wave video, is how to actually locate the epicenter of an earthquake. We're going to do a lab on this next week. We're going to go through the same methods that scientists use to determine, epicenters of earthquakes. It's really cool. Essentially, looking at these 2 pictures on the right here, they came from the previous section. We had that sample seismograph reading and our time scale here, our time travel graph, or travel time graph, if you will. And what scientists use is they look at the seismograph reading and they take the difference in arrival times between the P wave and the S wave. They take that time, they plot it on this travel time graph to get an exact distance that seismograph is from the epicenter. Now, the trick with this is you need at least 3 total seismograph stations to get an accurate reading. Here's an example of how this goes down, where I'm going to get my little marker here in a second to kind of help with this. So here's my marker. I'm going to pretend I am this blue chart right here, this blue graph. So using our difference in time between our P wave, and our S wave, the difference in time between the two of them. Or I should actually write this backwards because the S is going to be a larger number. So we take our S wave and we subtract from the P wave time to figure out the difference between the two. And that gives us the radius that we're going to be working with here. And we get that radius distance from that travel time graph. So let's say, for an instance, the travel time graph says I am 400 kilometers from the epicenter. So I take my seismograph station here. I use one of those pen compasses, you know, the ones that you put on a piece of paper to draw circles with. I put the metal point here, and then I position the edge of the compass with the pencil on the edge here, about, I think I said 400 kilometers. So we'll just say 400 here. That's how far it was. And then I draw the circle all the way around. So I know that somewhere on the edge of my 400 kilometer circle, that is where the epicenter of the earthquake is. And then I repeat that process 2 more times from data from 2 more stations, and where all 3 stations intersect, like right there, that's the epicenter of the earthquake. That's how scientists go about doing this. They use the difference in arrival times between my P wave and my S wave. Then they go back, take a look at the S wave, P wave chart here. They plot it, they figure out how far of a distance they are based on that P wave and S wave arrival time. They go to a map, they plot 3 different circles, and then where those circles intersect, that's where I get my epicenter. This is the process that seismologists use. It's really neat, it's really cool. We're going to do a lab on this next week. Our last slide, and this just kind of takes us back to what we've already spoken about in plate tectonics and volcanoes a little bit, is that the location of earthquake epicenters, they are closely corresponding to the locations of our plate boundaries, our tectonic plate boundaries. We learned before that most tectonic events, or earthquakes or volcanoes, all that stuff, the majority of them happen along the boundaries between 2 tectonic plates. That's why our ring of fire is so active. That's why the Mediterranean belt is so active. That's why the collision point between the Indian plate and the Eurasian plate is so active, because those are our boundary points, are very, very active players. So a lot of information in this section, but it's a really cool section. And I do encourage everybody to go back and rewatch this video, take down some extra good notes. If you have any questions for me, please go ahead and ask. If not, have a great rest of your day, and I will see you next time. Take care.